So up next we have Shreyansh Agrawal, who's going to discuss logarithmic soft graviton theorems from superrotation word identities. Go ahead.
Okay, so good morning and thank you for coming to this parallel session. I'd also like to start by thanking the organizers for giving me this opportunity to present our work that we did with Laura, Kevin and Homa on logarithmic soft graviton theorems from superrotation word identity. Now, the title has several parts, and throughout this talk I will try to break down into little chunks and finally stitch it up together. So let's start with why are we even looking at this now. Like roughly 10 years ago, when all this story of celestial holography was and holography in flat spacetimes in general was coming up, these relation between the asymptotic symmetries and soft theorems really played an important part in realizing what a picture could look like. So understanding these things beyond just the tree level becomes an important question to ask. But even further than that, looking at both of these things from their individual sides is also an interesting thing that one can ask. And finally, the superrotation particularly that we'll be looking at today is interesting from the point of celestial CFT because, okay, maybe I'll not go into details, but it corresponds to a celestial stress tensor for the proposed celestial dual for the theory. Okay, so the first part, of course, is the soft theorem, and let me go a bit quickly through this. So, of course, this is an old story where Weinberg showed that if you have a scattering amplitude with n hard particles and one graviton, and you take the momentum of this graviton to go soft, then you can factorize a divergent piece as 1 over omega, which multiplies the amplitude without the emission of this soft particle. This factorization is, you can further expand these amplitudes in loop orders, and this factorization holds to all order in perturbation theory. And also it's universal, as in it does not depend what you're putting on your external legs. This was a story and very old, but then very recently also Casazzo and Strominger continued this computation to not just the 1 over omega part, but also to the omega to the 0 part of the scattering amplitude. And they were also they were able to get this part. They were able to obtain the subleading soft factor, which here, if you look, is an operator that acts on the endpoint amplitude. Now you can write this subleading soft part as a projector acting on this n plus 1 point amplitude, which only projects out the subleading soft theorem, which multiplies the endpoint amplitude. This was the story, however, only at the tree level. At the loop level, then there was another computation which Sahu and Sen performed, and they just took the loop amplitudes, they took the tree amplitudes, and then they computed the full soft factor as a ratio of the n plus 1 point amplitudes and the endpoint amplitudes. What they found is that it's not just a 1 over omega and an omega 0, but you also have a log omega term in between. And now if you take the same projector for the subleading soft theorem, you see that it does not just pick out this S1 tree piece, but it also picks out the log omega term. So the full subleading soft theorem, if you would write with this logarithmic soft piece, you will see the subleading soft theorem, and you will see the log soft factor. All right, now let me, since I'm going to be talking about this in a bit detail, let me show you what it looks like. So it's a bit more complicated, of course, but for our purpose, we can write it in a more bite-sized form. And okay, this term was also obtained previously by Byrne, Davis, and Noel, but in a different avatar. It was sort of as a infrared divergence in the subleading soft theorem itself. But what's important, and what I want you to take from this, is that the log soft factor can be written as a sum of two pieces. The first term comes due to the interaction of the external soft particle with the loop, and the second term is the interaction of the external hard particles with the loop. Here these sigmas are some functions of the momentum, and these S0 and S1 are as before. Okay, so now with that we can really ask the question that can we account for this correction to the subleading soft theorem coming from the superrotation word identity itself. Now before that, let's look at what the superrotation word identity it is that we are talking about. So first, if we take a metric in asymptotically flat space-time, by asymptotically flat I mean if you do a large R expansion of the metric, you have a leading term which looks like the Minkowski metric, and then you have some subleading corrections. And these subleading terms have some have pieces that cannot be fixed by the equations of motions, which so they're really the free phase space of the theory. And then you ask, okay, what are the symmetries that preserve this fall off? So these symmetries were found out to be given by these super translations parameterized by the functions on the sphere, and super rotations parameterized by the holomorphic and anti-holomorphic functions. Now as I was saying that there's some free data that you can extract out of the metric. You can act with the diffeomorphisms and find out what's the action of these super translations and super rotation on the free data is. The one main part that I want to get to your attention is the C0 field, which is the goldstone mode of the super translation, in the sense that it transforms as a shift under super translation. Now once you have the metric, you have the diffeomorphisms, you act with the diffeomorphisms on the metric, you find out what the transformations are, and you ask, okay, what are the fluxes that act as canonical transformation on this phase space, and then give you these exact transformations. So it was found out to be the super translations and the super rotations. Again, you can ignore the details. The one main part I want to point out is that in the super rotation soft flux, okay, by soft and hard here I mean defined on either scry or defined on either the celestial sphere. So the super rotation soft flux, you can write it. There were some terms that were computed previously separately when they were trying to look at the subleading soft theorem as the word identity, and then there were some corrections which were computed when they were trying to look at super rotation as a canonical transformation on this phase space. So here we denote it by Fy soft 0 and Fy soft nu. We'll come back to this later. Okay, now that we have the charges, we can quantize them and ask what are the word identities of these charges. And to quantize them, we match it with the graviton field, and then by using the fact that the S matrix is invariance under the super translation, it means that it commutes with the super translation flux. So we just write the flux, we separate it into the soft and hard part, and we plug it back the mode expansion. And what one finds, of course, is that the super translation gives you the leading soft graviton theorem. And there is no problem in here. You have the soft graviton theorem, which is correct to all loop orders. You have the super translation, which gives you the full result. So this was just to set the ground on how we are expecting to do with the super rotation. Now, as I was saying, that there was already a part of the super rotation which was computed previously to compute the subleading soft theorem as a word identity. So when you take the super rotation flux, the Fy soft 0 and the hard flux, and you quantize the fluxes, you put it in the word identity, you derive the tree level subleading soft graviton theorem. Okay, this is good, but we know that we also have some corrections coming to this tree level soft graviton theorem because of the log omega factor. So really what we would like to see is this full soft graviton theorem coming from these fluxes. Now already the first hint is that we are, as I showed you previously, that we are missing one part in this Fy soft. So let's see what happens when we include the other part of the flux. Now the other part of the flux also depends on the super translation goldstone mode, and to compute the insertion of the other part of the flux, we should also know what's the insertion of the super translation Goldstone mode is. This was also computed previously, and you can already see that it has the divergent piece coming here. And now if you put in the Fi soft nu into your S matrix, you recover one part of your of your logarithmic soft graviton term. Now this is the part that comes from the insertion of the external soft particle with the loop. So the fact that you are getting a part that comes from the interaction of the soft particle with the loop comes from the part of the correction of the soft flux is, well, quite reassuring. That means now to look at the other part, you somehow want to look at what happens to the hard flux. Now look at the hard flux. We have to look at how to quantize the hard flux for the interacting fields, because really what we have in the bulk are fields interacting with gravity, and okay, thank you, are fields interacting with gravity, and when you take the long range limit of the fields interacting with the gravity, you don't end up on free fields, but you end up on some fields which are dressed with the Goldstone modes. So when you want to quantize these stress tensors should really not be the stress tensor for the free field, but for these interacting fields. So if you take into this, in account, you will have an additional term where, okay, this stress tensor rather is now for the free field. I'm sorry, it's a bit. So when you take in account for this interaction, you have an additional term coming from this dressing, and again you can ask for, okay, what happens when I put this term into the Ward identity for the with the S matrix, and you precisely recover the hard part of the logarithmic soft graviton theorem. So therefore now if you take the full superrotation flux, you take the soft part, you take the hard part, you take the correction to the soft part, you take the quantized hard part with the interacting fields, you in fact recover the full subleading soft graviton theorem, which has the full subleading soft theorem, which also has the logarithmic soft graviton part in it. Okay, so that was the main result of this analysis. But during this analysis, we also realized a few other things that I did not have time to go over now. So first of all, of course, as I mentioned briefly, that there was a story with the infrared divergent loop correction to the subleading soft theorem, which was of course just the logarithmic soft theorem being looked at from a different perspective. Then secondly, in the infrared factorization of the amplitudes, there's a real and an imaginary part, and to also account for this imaginary part, you have to modify the 2-point function of the Goldstone mode of the super translation with an additional imaginary piece. And finally, taking everything in account, we are able to reproduce the full subleading soft theorem from the superrotation fluxes. But that's about it. But I'm just going to put this last slide here because there's not just one soft theorem, but like if you there's an entire family of them, and you can ask a lot of interesting questions about this, and I'll just mention some of this here. So thank you for your time.
You have a minute if you want to explain some of the bullet points.
Okay, like we can ask, for example, like how can we get these higher log corrections from the tree level for the higher soft theorem in the similar way we can get the log omega from the omega 0. And then there's a story with the W1 plus infinity algebra at tree level. Can that be generalized to the higher loops? There's already some work for here. One can ask, okay, this correction that I was mentioning to, how does it affect this celestial stress tensor? And further, okay, this was what Sungmin was already a bit talking about. What are the bulk diffeomorphisms related to various soft factors in the higher point of these terms?
So questions?
Yeah, thanks for the talk. When you were showing us the expressions for the fluxes, I was wondering, so you said that some pieces had been neglected initially, but then were added up. So what was a bit the story there? Is it,
So
I mean, why were they neglected in the first place?
These pieces were constructed using the subleading soft theorem. So by asking what's the flux.
So going backwards from the soft
Yeah.
theorem. And also another question related to this slide. There is also another paper by, I think, Compare, Serrage, Olivieri, where they also give expression for the fluxes of BMS charges. So is this the same, or maybe?
I have not.
Okay, let's chat later. Another very quick thing, going to the end. So you saw that there was a piece in the imaginary part that is here in this slide.
Yeah.
You said it was previously disregarded. I mean, do you mean in your slides or like in the literature that there was?
In the literature.
So you mean in the Sahu Sen papers, there's a missing imaginary
not
part?
not in Sahu Sen paper. In the celestial, in a lot of paper talking about the. In the Sahu Sen paper, this piece is there.
Okay, so the infrared factorization formula for the amplitudes are correct in the literature.
Yes.
Okay. So you mean it was neglected in this correlator?
Yeah.
Okay. So- And then maybe a comment. So the last slide. Recently, there has been a proposal for all these 1 over omega, log omega, omega, log omega square. So that's diagonal.
Yeah.
In the case of a 2-to-2 hard scattering, and for the classical limit, there is a proposal in papers by Michael Abruzzo and I, and also some others by Rudolf Russ. And so there is a formula that resums this log omega. So maybe it's interesting. Yeah.
I'll look at it. Thank you.
Any more questions?
Yeah, on this last slide, so I guess we are looking at the second line here, but now if we go further to third and fourth lines in the table,
Yeah.
so I guess in your story you would have the fluxes that correspond to the first column, but now we have divergent corrections that give you the second and third column. Do you have an idea what they would look like? I guess you have epsilons, the Dimreg regulator. So do you think the second and third column would look different from that point of view?
Like 1 over epsilon and
1 over epsilon
m
squared, or
yeah.
okay.
But we don't even know what are the fluxes for such subleading
Yeah.
tree level.
Even the first column.
Yeah.
Okay.
Any more questions?
I mean, just if you can clarify the additional contribution in the previous slide. It's like, why do we have it as in the form of this I pi delta eta eta? Like, is there a reason why this is the required correction?
Yeah, so you can, if you look at also the Weinberg's original paper where he does the soft factorization. So
Everything is that paper from
Everything.
65.
Yeah.
I was very surprised.
Okay, so it's just that, right? It's just
yeah, it's just I think it's called the phase in that paper. So yeah.
It's the last section.
Is
before
that exactly.
No one cares. It's a phase.
Yeah,
so
it's
who
a
cares
phase,
about
but-
phases? And then it built up. There's somewhere in between.
Yeah, for him it's a parenthetical remark. By the way.
But everything is there, of course.
Okay. If there are no more questions, then thanks for listening.
Thank you.